All right, welcome to hydrogeology at University of Montana. And today we're going to be finishing up groundwater in the hydrologic cycle. And yeah, so a couple items of business. Like I said, lectures have been posted. So I will from now on record all my lectures and they will be posted as I get them up onto the web. They'll be on the Moodle site. Let's see if I can still go there. Yeah, so things are being done by topic. So if you hop into the groundwater and the hydrologic cycle section, I don't know, why is it not moving? Huh. Oh, because I'm in it. You open that section, there's a page with recorded lectures, and there'll be a link to all these lectures, right? So the makeup for Tuesday is posted, and it talks about this evapotranspiration problem. So it's probably worth watching. And then the other ones are there if you want to review them later in time. And of course, if there's any reason that you need to miss class or you can't come to class, then talk to me and I'll give you the Zoom link to Zoom into class. So like Finch is zooming in for a little while. So it's totally doable now. I think it'll be pretty easy for us to have some people join via Zoom or in class. My preference is if you can make it to class, to do class, but the option is there. We're flexible now that we're recording on Zoom. Any other business I wanted to get to? I think that was it for now. So I want to cover this this last lecture topic of groundwater in the hydrologic cycle. Should get it done today. And if we finish early, we'll see. I always think I can do things faster than I can. But if we finish early, then we might have some time to do a little question and answer on the homework at the end of the day. We'll see. I better stop stalling and get to work then. Okay, so we're gonna start off and think about groundwater's role in stream flow. And I want to start this conversation off with taking a minute here to ponder a question. And my question is this: why is the Clark Fork River still flowing? What's that? All right. So the answer is the only reason why we haven't had any rain for a little while appreciably. The snow melt in the mountains is not happening. It won't happen for another 3 months. All right. The only source of water in the rivers in the winter is groundwater. All right. So one way to sort of help you get a feel for how active the groundwater is just to, when you go over these rivers, realize that right now their only source of water is the groundwater. That's it. All right. So that's an indication of how much groundwater circulation is occurring up in the mountains at all times. All right, so we're gonna talk about the hydrograph today and what happens to precipitation or snow melt on a hill slope. So first thing I want to do is sort of consider a generic hill slope. So here we've got this hill slope, and it's going to head down to a stream down at the base. So here's my stream, and put some trees on here. Some shrubs. And we're going to give this hill slope a pretty generic but common structure that we think of hill slopes having. And that is, we've got a shallow layer of soil. All right, so here's my soil layer. And this soil layer sits on some kind of bedrock. And we're gonna have some a cloud up here. And we got some precip falling on our hill slope. Now, this could be precipitation, or you know, in the mountains, precip and snow melt do similar things. So I'm going to call it precip for now, but actually, you know, snow melt is sort of the same thing. It's a flux of water to the ground surface. All right. And actually, for us in the Northern Rockies, that's probably our biggest flux of water. But we'll just consider precip for now. Okay, so we've got this precip, and it hits the surface, and sort of, I'll say the main subject area of terrestrial hydrology is what happens to it now, right? What is the main thing that happens? And we're going to look at a few different processes. So we talked about some of these. So what are the ways during the storm that what happens to this water when it falls on a hill slope? What are some processes that we talked about? Sure, infiltration's one of them. Okay, so we got overland flow. If it infiltrates, what happens to the water? Yeah, if it infiltrates down here, it can pool on the bedrock surface, and we're going to call it soil flow. We get soil flow moving through the soil down to the river. All right. And then some of it can recharge down to the aquifer, and we can get groundwater flow through the aquifer into the river. So we have soil flow here through the soil column. We have overland flow across the top, and then we've got groundwater flow coming into the stream. So this groundwater flow is the main topic of our class, right? Once it gets down into this deeper aquifer. But during a precipitation event, these other two processes are present. We have overland flow and soil flow. So um, to give you guys a bit of a conceptualization of this. So first of all, let's just talk about overland flow for a second. Um, and it's a mythical creature. It does exist, but it's hard to find. And for a long time was sort of the basis for a lot of watershed hydrology was this idea of overland flow. And the idea was this, your soil has an infiltration capacity. So F we're going to call infiltration capacity. All right. It can only soak in water. It can only allow so much infiltration, right? And actually that infiltration capacity changes through time. So a civil engineer named Horton back in 1933 proposed this kind of a model for infiltration capacity. It started off at a relatively high level that we're going to call F naught, and then it decayed down and then hit some long-term capacity that we're going to call FC. All right, so as soon as you started raining, the soil is dry and it has a lot of reasons to pull water into it, and you have a high infiltration capacity. As the soil saturates and gets wetter and wetter, it has less forces pulling the water in, all right? And you reach what we call the long-term infiltration capacity, and your soil can basically only let a certain amount of water through, all right? So the idea with Horton overland flow is that if your precipitation, even if it starts off sort of below the peak infiltration capacity, but if it continues in duration, so this is precip. When the precipitation exceeds my infiltration capacity, that means I'm adding water faster than it can infiltrate. It's gonna flow over the land. So when precip is greater than F, we get overland flow. And this does happen. It does happen. It is in a natural hill slope rare. The infiltration capacity is high enough that in many places, you know, it's not a predominant way of generating stream flow, but it does happen. So overland flow is when my precipitation increases above my infiltration capacity. Okay, let's move to soil flow. Okay, actually, one thing I wanted to before we move to soil flow, we'll talk about this in more detail, but just to mention now, overland flow, as soon as my precipitation stops, all right, then my precipitation rate is no longer greater than my infiltration capacity. And so my overland flow stops pretty rapidly after my precipitation stops. All right, so overland flow really only happens during the precipitation event. It doesn't extend past the precipitation event. So S, or soil flow, I'm going to zoom in on our on a section of our hill slope here and just sort of enhance the resolution. So I got my soil overlying my bedrock here. All right, and I have water that infiltrates here into my soil. All right, so some portion of that precip always infiltrates. And it migrates down through my soil. And if there's a contrast in the properties between the soil and the bedrock, we'll talk about what properties those are later. But if there is a contrast in these properties, the water will pool on the surface of the bedrock and flow down the hill slope along the bedrock profile. All right, and the main key here is there has to be this contrast. The bedrock has to be different than the soil. So if you're on a big sand dune, you would never see soil flow. All right, you've got to have bedrock and soil, and they have to be different. When that happens, the water pools on this bedrock interface and it moves down slope. All right. And then some of that water, some of that pooled water will then infiltrate the bedrock and become recharge. All right, hit the groundwater system and move out. Okay, so just to give a bit of a, give you guys some kind of conceptual image in your head of what this looks like, I'm going to show you a little movie here. And so let's introduce this model. So this movie that I'm going to give you are results from a numerical model that models the flow of water in the ground. All right. And the model looks like this. It's a block that's tilted. So it's a hill slope. And the top 2 meters of it are soil. And then the bottom 90 meters of it are, or 98 meters of it are bedrock. All right. And there's a contrast in the properties between the soil and the bedrock. And then what I do is I apply snowmelt and precipitation taken from actually a snowtel in the mountains near Missoula, which is an instrument that measures precipitation and snowmelt in the snowpack. All right. So it's basically I'm applying infiltration, and then what happens is the model produces the distribution of water in the hill slope. All right. And so let's go and watch this video. And there's 2 different models here. let's just, for us right now, say that the contrast between soil and bedrock is different. In this model, there's less of a contrast than in this model. All right. Okay, so in the Northern Rockies, we get a big pulse of water in the spring during snowmelt. Then we get some smaller rain events for the rest of the year, but it's that big spring event that's the number one generator of infiltration in our system. So when I hit play, what you're looking at, the colors are essentially the degree of saturation. So down here, this is the water table where everything is full of water, and where it's red, there's water and air in the pore space, right? And what you'll notice is that during the spring, you're going to see this wedge where the water wets up along the bedrock interface and becomes soil flow. Some of that water now moves down into the groundwater system, all right, becomes recharge. But some of that water, that when it saturates up in the soil, it's going to do it here again in a second when we have another spring event. Some of it is moving down slope along the soil zone and into the water. And then some of it is recharging this groundwater system. All right, and you can see the same thing happening in this one. It's a little more, the configuration changes depending upon the contrast. So this is just to give you guys some sort of conceptual idea of what the saturation or the water movement looks like in a hill slope. It's saturating up in the soil, all right, and it saturates quite a ways up the hill slope. And then some of that moves down into the bedrock, becomes recharge, and recharges this groundwater system. Now, during the summer, you'll see the soil dry way up, all right? So the soil dries up and the groundwater table configuration basically stays pretty much the same. You see a little bulge during the spring and that drains down a little bit, but the groundwater stays very stable. And this is 10 years of sort of spring snowmelt and then summer precip and dryness. Okay, so what we're going to do now is talk about how we can use how these different processes manifest themselves in the hydrograph, all right, or in the measurement of stream flow. So if I was to come down and measure stream flow, how does one of these big input pulses like a spring snowmelt or a big rainstorm manifest itself in the hydrograph? So what is a hydrograph? Okay, so Mark's given us some idea maybe of the shape, but at its fundamental, it is time, right? Versus what? Yeah, so for a stream, it's the discharge or the amount of water moving in that stream past a point. All right, so Q is discharge. All right, this is volume per time. All right. And it is the volume per time moving past a point. So it's Q is the volume at a given stream cross section. And if I wanted to sort of zoom in a bit on a stream cross section here, here's my stream. All right, and it sort of winds back into the screen here. So what I'm looking at is the volume per time flowing out of the stream across a plane like the board here or the screen. So this is Q. All right. So how do we measure Q? What's that? We do use a gauging station. That's a very valid point, and we do that, but the gauging station doesn't actually give us discharge. What does a gauging station do? Gauging station is it's like a staff we put in the water here. And what it does is measure the height of the water. So we're not even going to get into how we turn that height of water into discharge, but fundamentally, how do we measure discharge? What do you think we do? Okay, so you said one thing that was very important, velocity. All right, so Jenna, I know you've gauged streams. What do you do? Yeah, so when you go out and gauge a stream, you go out here and with an instrument and you take at a bunch of points in the stream and a bunch of depths. You take the velocity with a flow meter. All right. And you figure out the velocity of the fluid movement here. So the first thing we do that Bailey mentioned was velocity. And then this has what are the units of velocity? Velocity is length per time, right? I need this to be length cubed per time over here. So what am I going to multiply this velocity by to get the discharge? The area, right? So the morphology. So when we do a discharge measurement, we do two things. We measure the velocity and then we measure the stream width and the depth profile, right? So the discharge is equal to velocity times area. And this is a key equation. We're going to talk a lot about discharge. We'll use another term called flux, all right? But at its base, discharge is velocity times an area, all right? Okay, so when we have a hydrograph, we're measuring this discharge, all right, at this one place over time. We do that through what we do is we measure height because that's easy to measure. And then we go back every month and we measure the discharge. And we create a relationship for this point that relates the height of the water to the discharge. And that's called a rating curve. There's lots of ways you do that, but fundamentally, we have to come out here every month or so and actually measure the discharge. And then what we monitor, because it's easy to do, is the height. And we just create a relationship between the two. So what we get is a hydrograph, and it measures the discharge. And if we have a precipitation event, we might see our discharge come up, and then it'll come back down. And then we might get another one, it'll come up and it'll come back down. So this is the hydrograph. It is the measurement of discharge in this stream at this point. So let's consider our hill slope again and think about what the hydrograph looks like during a precipitation event and how the different sources of water that we've just talked about contribute to our hydrograph. All right, so we've got a precipitation event. So we've got overland flow. We've got this soil flow. And then we've got groundwater flow, all discharging to this stream. All right, so our overland flow, our soil flow, and our groundwater flow. And I will put some triangles on here to indicate the water table. So if we were to look at the hydrograph during a storm event, all right. So here's my discharge at this point versus time. And during a storm event, so before the storm, we're draining our watershed, our discharge would generally decrease. And then we get a storm event, and that will increase the discharge. It'll peak. So this is right here. This is sort of the time that the precip begins. And then the precip ends. And that'll be pretty close to our peak discharge. And then after that, the stream will gradually recess. And by recess, we mean the stream discharge decreases. All right, so in between precip events, we have recession periods. Now, if it's been a long time, since precipitation, all right, like it has right now, it hasn't been a long time since precipitation for us, but it's been a long time since we've had precipitation that adds to the stream flow budget. Then all of our water is coming from groundwater, and we call this period here, a long time after, we call this base flow. And base flow is marked by really low rates of recession at low levels. So it's really low flow, but the discharge isn't changing much. So low flow and small recession, or a flatter curve. Okay, so the hydrograph is this awesome signal. It contains information on all of these processes. So when we're measuring the discharge in the stream, we're measuring overland flow, we're measuring soil flow, and we're measuring groundwater flow. All right. And it's also very accessible to us. It's pretty easy to go to a stream, install a gauge, and measure discharge. So there's a long, long history of a branch of hydrology that we call hydrograph separation. And that is trying to take the hydrograph and pull out these different components, figure out how much of the water is coming from overland flow and how much is coming from soil flow and how much is coming from groundwater flow. And for us in particular, groundwater is really hard to measure. It becomes a way for us to try and estimate, come up with estimates on the volume of groundwater flow, and importantly, how much recharge the groundwater system got. So if we were to separate this hydrograph sort of conceptually, we might come down and do this. And here I'm going to use overland flow. So overland flow at long times after precipitation is 0. All right. So it's 0. I'll use green for overland flow. It's 0, it's 0, it's 0, it's 0. Let me extend my lines of when the precipitation begins and ends. All right. And sometime probably a little while after precipitation begins, we've exceeded the infiltration capacity and we're going to start some overland flow. All right, so our overland flow comes up. All right, it probably peaks, you know, stays pretty constant, but then almost immediately after the rain event ends, the overland flow comes right back down to 0. All right, so it's very short-lived, and it's only during the precipitation event. All right, I'm going to come down and now look at soil flow. So soil flow is probably low or 0 during times where it is really dry. All right, so a long time after precipitation, our soil flow is pretty close to 0. We have to infiltrate the water before it'll run off, so it's probably a little delayed compared to overland flow, maybe. And it sort of is going to increase. All right. It's probably going to peak pretty close to when precipitation ends. But now we've filled the soil up. All right. We got 2 meters of soil. We filled it up. And it's going to take a while for that to drain out. Right. So if you think back to that movie, the soil would wet up and then it would take a while for that wetting front to dry back down. So soil flow continues for some time after the precipitation event and then goes back down to 0. All right, so it's longer lived. But does go to 0. All right, so finally, let's look at groundwater flow. All right, groundwater. Well, it's not zero because it's the only source of water if we have a perennial stream. All right. Once precipitation starts, we will start to get some recharge and we will get a bump in the groundwater. All right. It's not a lot, but we will get a bump. That recharge will probably continue as that soil water continues to infiltrate into the groundwater system. But then it'll come back down, all right, and start to recess. So groundwater never goes to zero, but it gets a smaller amount of the water during a single precipitation event. All right, so we can sort of think about these different processes and the time scales on which they occur. So overland flow is directly during the precipitation event. It is within hours after the precipitation ends, overland flow is done. So this is like on the scale of hours to days, maximum. Soil flow, you know, we've filled this full soil column. It might take a while for it to flow out. We're talking days to months, all right? And groundwater flow, if we're in a perennial stream, there's continual groundwater discharge, all right? Now, what importantly for us as groundwater scientists, one of the main things that we're interested in is recharge. How are we going to figure out how much recharge we're going to get? And one of the ways we can do that is by looking at sort of this change. This, you can think about it, this change in discharge here has to be due to the recharge. And so we're going to use hydrograph separation to try and estimate the recharge. Yeah, good question. I mean, groundwater, it depends, but we're talking months to years generally. And if you're in a perennial stream, it never drains out. It's years to decades. So in general, I kind of think of these as sort of as a crude approximation. This one's days, this one's months, and this one's years. Now, I'll just say there's a whole branch of hydrology that's essentially devoted to trying to pull out the signal of these three different processes. And we do that both through the discharge alone, and we also do it through the chemistry of that discharge. So you could imagine that, rainfall has a different amount of chemicals in it than water that's been underground for a long time. And so we can measure not only the discharge in the stream, but the chemistry of that discharge and try and back out these different components. We're not going to try and do full hydrograph separation in this class because we're focused in on the groundwater. What we're going to try and do is focus in on what happens to the base flow, and can we use that change in base flow to estimate the amount of recharge we got to our groundwater system. Okay, so this is a logical place to have a little break here before we get into this method that we can use to estimate recharge. So let's take let's do I don't know, 5-minute break. So 9 9:43 or so, we'll get started again. Okay, so I'm going to zoom out here and draw another hydrograph. And let's just say we're gonna start figuring out how we can use the hydrograph to calculate recharge. And the basic idea is this. So here's just sort of a generic hydrograph. And we start off during a recession period, we get a precipitation event. Our stream flow goes up, comes down. Whoa, what just happened? Starts to flatten out. We have a long recession period, and then our stream flow comes up, comes down, and then we enter another recession period. So this portion here, where we have sort of this linear recession, this is our base flow. And we make the assumption here that this base flow is groundwater. All right. Okay, so if this base flow is groundwater, all right, this is sort of our linear decay during groundwater discharge. And if we were to draw this curve as if we had no precipitation event, our groundwater would just keep going on this track, right? And this would be our discharge later in time. If we had no recharge event, so this is the all right. So we could actually extend this line out to infinity, and we could calculate, if I took the area under this curve, this would be a total volume of groundwater I could discharge. If I extended this line out to where the discharge equaled to 0, I could calculate the total volume of groundwater discharge. All right. So this area under this curve would be the total volume of groundwater available to discharge to my stream. before my recharge event. All right, and I could come here and look at this being the volume of recharge that is available to discharge after the recharge event. Right, so this, if I extended this line, this would be the volume that I'd have after the recharge event. So the fundamental idea here is I'm just going to compare. Actually, I'm going to essentially just compare the area, this purple area, which is the area or the volume of groundwater that could discharge from this time here. Let's call this time T sub C. T sub C. I'm basically just going to compare this volume, which would be the volume if I didn't have a recharge event that could discharge, to the volume after the recharge event. And I'm going to say the difference between those two volumes is the recharge. So we call this the recession curve displacement method. All we're doing is taking this recession curve, we're comparing it to the next recession curve, and we're looking at the displacement between these two. And we're using that to calculate the recharge. Right, so fundamentally, that's what's happening. So it turns out that we're gonna make a couple assumptions. So we assume that groundwater decay comes from a linear reservoir. And what do I mean by that? Is that Q is equal to Q naught E to the minus alpha T. This is the groundwater recession curve. And it is described essentially as an exponential decay. All right. And so if I have a hydrograph, so there's a couple reasons why I point this out. So if I plot the logarithm of Q versus T, So here, if my hydrograph is plotted on log, on a semi-log axis, so this is log of Q, and this is T, this equation will plot as a straight line, all right? So what I'll see is that my water will increase, and then I will get these very straight lines during groundwater discharge. Right, so that's how we identify these areas or these times of groundwater discharge, by this straight line when we plot on log paper. The other thing that assuming this form of an equation does is it allows us to integrate the curve and come up with some pretty easy equations for the total volume of water underneath the curve, all right, underneath the curve. And I'm not going to get into, in the past, I've gotten into the mechanics of that integration, and I think it's better just to focus in on the mechanics of making this recession curve displacement method work. But regardless, to say that the basic idea of the equations that we're about to go over and the method that we're going to go over is that you integrate this curve, you figure out the total area underneath the curve, and you do that for the water as if there wasn't a recharge event. And then you do it for the water after the recharge event. You subtract the two, and the difference is the recharge that you got. All right. So in practice, we're going to use what's called the Rorabaugh method. And the basic idea is that we have a plot, the log of the discharge versus time, right? And it's going to look like something like this. All right, and we've got these two straight line sequences. And if I was taking my time a little more, those ought to be the exact same slope. And the idea is this: we fit a line to base flow recession curve before event. All right, so here that's going to be this one. So we would come in here and we would take a ruler or use our computer and fit a line to this guy. Okay, now we want to calculate. So the slope of that line has something to do with this guy. All right. It's, if I plot this in log space, the slope of that linear line will be something to do with this recession constant. But so what we're going to do is we're going to fit this line and we're going to calculate the slope. And this gets called, so we calculate the slope or the recession index. So this we're going to call K, and K is the number of days it takes for the flow to reduce by 1 log cycle. All right. I got a hydrograph here, which is actually the hydrograph from your homework. And right now we're going to talk about this, and everybody take notes and pay attention because everybody's going to have this same question. Every year I get it from basically everyone in class. So how do we do this? Well, let's go and let's look at a hydrograph here. First of all, we're gonna take a step back here, and some of you will have experience reading log graphs and some of you do not. And it always is a hassle and hard to remember if you don't use them a lot. So this is a log graph, and you can tell it's a log graph because my major indicators jump by a power of 10. So this is 10 to the 1. What's 10 to the 1? 10. What's 10 to the 2? 100. What's 10 to the 3? 1,000. Okay, so each one of these major increments is jumping by a power of 10 or just adding a 0. All right. Okay, that's great. What is the value of this line right here? Yeah, the second line, the one that my mouse is on. What's the value right here of this mark? Everybody get that? That's 20. What's this one? 30. So we're counting up by 10. So 20, 30, 40, 50, 60, 70, 80, 90, 100. Got it? What's the value of this line? 200. What's the value of this line? 300. Now we're counting up by hundreds. So 200, 300, 400, 500, 600, 700, 800, 900, 1,000. All right. Now on this line, we're counting by thousands. All right. So this one would be 2,000. All right. Up to 10,000, then we'd go on. Okay. Now, what do I mean by a log cycle? A log cycle is, for example, going from 1,000 to 100. So that is a log cycle. All right. We could also have a log cycle that goes from 20 to 200. That's another log cycle. All right. It's increasing. What a log cycle means is increasing 1 order of magnitude or adding 1 0 to the number. All right, so if I wanted to fit a line, so my step 1 is to fit a line to, say, this recession curve. And you can eyeball this. There's no right or wrong way. And I will tell you this right now, when I grade homeworks, I'm not here to quibble, all right? I am not gonna say, hey, I think you could have fit that line like a little tiny bit better. If you give me this line, that does not fit the curve. And I will say, no. But if it's anywhere close to fitting it, it's okay. I'm not gonna, we're not doing this with hardcore math. We're not any of us guaranteed to have the best fit unless we do it with math. So if it's close enough. All right. So I fit this line. and I extend it. Now, I want to know the number of days it takes this line to go over one log cycle. So the trick here is just to pick a couple spots where the line crosses, intersections. So for example, right here at 100 days, we're at something like, here's 200, 300, 400, 550, right? So at 100 days, I'm at 550. And so one log cycle from that would be what? One log cycle down from 550 would be what? 55. So then I want to find the place where my line crosses 55. So let's find that line. So this is 10, 20, 30, 40, 50, 20, 30, 40, 50, 55, somewhere right around here. So at roughly 650 days, I crossed 55. And at 100 days, I crossed 550. So how many days did it take me to go that log cycle? $550, that's 650 minus 100. It took me 550 days to go from 550 to 55. All right, so that's the number of days it took me to go one log cycle. So that's it. That's my K. So if I go back here, my K is I fit my line and I figure out how many days it takes me to descend one log cycle in flow. And that gives me K, which is my recession index. All right, so I calculate K from this line. Now, there are some properties of this integral, but the first thing I'm going to do, the next thing I'm going to do is I'm going to identify the peak and discharge. All right, so here's my peak and discharge. Now, I want to move off of this peak some known value or distance, and then I'm going to calculate the difference between these curves. All right. So the key here is we want to calculate this critical time that we're going to move off of the peak. This is kind of the key to the Rohrabaugh method. And the idea is that if I move a certain distance off of this peak, then it's very easy for me to calculate. We move a certain distance because the difference in the integrals between this one and this one algebraically simplifies to a very simple equation. So the key is the distance we move off of the peak. This is actually like the full key of the Rohrabaugh method is just move off this peak a certain amount And then the difference between the integrals of these two exponential curves becomes a very simple algebraic expression that you're going to see. All right, so that's the idea here. So this is TC, and TC is, we find from the recession constant, it is 0.2144 times K. All right, so I take 0.2144 times K, and I get this distance TC. All right, so then I'm going to draw a vertical line, TC days, off of the peak discharge. All right, so I'm just going to come over here. I calculated TC, and I just draw a vertical line here. Then from my vertical line, I'm going to pick off So QA is the discharge on my recession curve as if there was no recharge event, right? So discharge on my fitted recession. Oh, geez, I can't spell. All right, it's the discharge on my fitted recession curve at this vertical line I drew at time TC past the peak discharge. So key here, you got to extend. You need to make sure that when you draw this line, it extends to both ends of the graph. All right, you pick off QA. The next thing you do is you pick off QB. This is the actual discharge, all right, where it crosses this vertical line. All right, and now, because we went to this magical time TC past the peak discharge, and the integrals under this curve and this curve have this sweet geometric relationship, then we can calculate the recharge very easily. Using this equation. R is equal to 2 times QB minus QA over 2.303 times K. And this recharge is what I want. All right. .303. You don't necessarily have to have this 03 here, but I'll clean that up. Okay. So that's it. That's the basis of the recession curve method. Now, you're going to do it by hand for one sort of big recession curve displacement from snowmelt in Rock Creek. If we wanted to do this for like a whole watershed and we wanted to calculate the recharge from every single rain event, then we would use a computer program. And the computer program is going to spend a lot of time trying to identify recession periods. And then it calculates sort of what we call the master recession curve. So basically the recession curve that best fits all the different recession things it identifies. And then it does this same thing. It goes TC past each peak and calculates recharge by the same method. So we're going to do it once by hand, but if you wanted to use this in real life, you would use it. There's various computer programs written for this recession displacement method, or the Rorabaugh method. And one of them is produced by the USGS, by Rorabaugh himself, and you can use this computer code, and it reads in a USGS hydrograph, and you play around with it and you do this. Okay, so we got about 20 minutes. I'm also starting to run out of battery, which is not good. Before I open it up to questions, I wanted to do one thing, and that is to give you guys an example of how I want you to present your problem answers. All right. And we've talked about this a bit before, but I want to do that here. So and let's let's go back to this problem I gave you guys. So you have this watershed of Rock Creek. All right. And you have the value of precip at a bunch of points here. right? And I ask you, and so you've got, you know, P1 and all the way to P sub I. You got a bunch of precip points. And so I ask you to calculate the total volume of precip, for example, or the average area weighted precip using Tyson polygons. So let's do that. So my question might be, the question states, what's the average precip using Tyson polygons, right? Okay, so we've gone over this in class. What were sort of the method? What is the basic method that we do when we're using these Tyson polygons? Yeah, it basically boils down to finding the midway point between each station. So we would sort of use this map. We connect all the adjacent points together. And then we draw these polygons around each point. All right, and so you would do something like this. You would create this Tyson polygon map. All right. Now, if I have that map, what do I do? Yeah, there was an equation that we could use. So here's how the outlook would look. You would do this work. You would do this work. You would make this map. So when we present it, here's the basic outlook. It says, so this would be whatever it is, number 2A. I don't think this is the right number. I'm just making this up. Problem here, I got a better idea. I'm gonna make it up, I'm gonna make it fun. All right. Given, this is my first section. Now you're gonna tell me everything you're gonna use here to solve this problem. All right, so things I've been given. Given one map of precip, 2 precip values, P1 to P sub I. What's another important piece here? Well, that formula for the Tyson weighted area average, P_av is equal to the sum P sub I, A sub I. All right, so this is my basic equation. I've said I've been given these precip values. I've been given this map. Yeah, no, you can just point to the map, but you've been given the precip values. Here's the equation. Probably something else that you're going to need here is how are you going to calculate area? Okay, so graph paper, but so how are you going to do it from the graph paper? Ah, given the scale. Oh. All right, so I've these are all the things, all the ingredients you're going to use to solve your problem. And then the next section is find. Well, here it's pretty easy. What am I finding? I'm finding P bar here. Okay, so the final section is the solution. And the point here with the solution, so you've already given me everything you're going to use. You've told me what you're going to find, and now you lay out a roadmap. All right. And for a lot of these, you may be doing work on computers. You might, like a lot of this work's done on the map. All right. What I want is a step-by-step roadmap of what you did, and then you can point to where you did that. So step one, using map, which was my given number one, find midpoints. Step two, using midpoints, draw polygon around each point P sub I. All right, this is just listed out. It's easy for me. I can see, oh, Tess started off with midpoints, and then she drew polygons. Even if you mess up the midpoints, I know what you were thinking. It's easy for me to understand what you were thinking. And, I don't know that I got all the midpoints perfectly correct. All right. If I know that you're on the right track and you make a small mistake, that's a very different thing than me being like, I can't even figure out what you were doing. Right. So the clearer you are, the better. All right, step three. Using scale, which was my given number four, calculate A sub I for each polygon. And you could say, see work on map or wherever it is. Or if you want to do the work here, do it here. You could sum up all the square. If you're using graph paper, you can sum up all the squares right here for all of them. All right. Step 4, using P sub I, which was my given number 1 or given number 2, and A sub I from step 3. Oh no, it's not 48. It's 42. Clearly box your answer. All right. So my steps lead directly. This was given number 3, I think. And then I calculate this. Now, how much of the work you want to show here? Like if you're going to do this by hand, sure, put it down here and show your calculation. If it was me, I'd probably do that calculation in Excel or something like that. And I might not show it. I will look at this answer and I will look at your equation. It's better for me. The more work you show, the more I can be like, oh, they made an arithmetic error. But what I really need to be able to do is track what you were thinking you were doing. All right. And I will check your answer first and I'll see, well, did they get to 42? And if they didn't, I'm going to try and figure out where you went wrong. All right. I don't really want to get in here in the guts of your arithmetic. What I'm going to look at, I'm going to say, oh, they had all the P sub i's, their A sub i's look okay. They just messed up this equation. They didn't make their calculation right. I don't have time to grade at the resolution where I'm like, oh, you didn't add these two numbers the right way. All right. Okay, so the main things are you list your given, you know, what you're going to use to solve the problem. You list exactly what you're going to end up with. All right, P. And then the solution is you step all these steps, and then I end up at the thing where I said I was going to find. Now, this is going to be a hassle, but it's actually going to do two things for you. It's going to help you develop your ability to describe how you're solving a problem. All right. It will actually also help you start to logically lay out how you're going to solve these problems. All right. And in the end, I still use it when I have to solve a hard problem because it helps me more clearly define my path. All right. It's also going to make it a lot easier for me to give you all the credit you deserve. So it's really hard for me to read your guys' minds. All right. And when it's not laid out, it's really hard for me to be like, what was Mark Real thinking right here? All right. It's usually impossible for me to figure that out. But if you lay it out, I can say, oh, well, that's an interesting thought, you know, or it's a totally crazy thought. But either way, I know what you were thinking. Or Mark was completely on the right path. He just didn't add right. Right. So, okay. Yeah. Hold on. You, and then I'll get Tess. Um, for now, I would just say calculate it on Excel. For this problem set, that's fine. If there's actual problem sets where I want you to, and there will be some where we're actually making, using Excel and sort of making coding kind of things, then I'll want to turn those in. But for this problem set, this is all arithmetic. It could be done on a calculator or Excel. I don't care. I don't need to see the mechanics of the full equation. No. Yep. Tess. You can, I would prefer, you could use Word and just print it out and attach it. I was going to say another thing is I will ask you both for an analytical, sort of number, and then I might ask for some analysis of that. And so a final section could be analysis. You know, this number is greater than 41, whatever I asked for, right? But yes, feel free to put that on Word, print it out, and just put it, but just make it so that it's, what I don't want is like all your graph paper and then random answers in Word attached at the end, and I got to figure out where those sit in the lineup. As long as it's logical, I don't care whether it's, but the calculations, drawings, those should be done on graph paper. All right, Finch, this is probably going to die any second, so I'm sorry, but I think we're pretty much done. If you guys have questions, I'm happy to entertain them. We have a few more minutes. And Finch, I'm sorry, but my computer battery will die any second now. Yeah, Tess. Right. So it doesn't for PET, for calculating PET, but it does, like I ask you, for example, if, well, I can't remember exactly what I ask. I think I have that pulled up. All right, calculate PET. Discharge doesn't matter at all. Yeah, you don't need discharge at all. Sometimes you'll get information that you don't have to use.